Yeah, thanks, Rebecca, for that introduction. Hi, everybody. I know a few of you there at Berkeley. I'm sorry I wasn't there. I'm not there in person, but I'm so glad that Zoom can connect all of us anyway. Okay, perfect. I suppose everybody is familiar with the LHC Grand Challenge. We are operating our detectors in an extreme environment where the total ionizing dose is about more than a gigarad, and we have to be concerned about single event effects. Along with that, we produce a very large data volume, so there's generally a billion sensors and a billion collisions per second producing raw data in petabits per second. But most of this data, like more than 99% of the data generated, does not provide useful physics information when we are looking for something very specific. The occupancy of the detector or the vertex detectors is roughly in the order of about 3 gigahertz per centimeter square, which basically means that you want to create more granular detectors, which in turn increases your data volume, which has implications on your power consumption and requires more complex on-detector electronics. So for this upgrades, beyond the phase 2 upgrade, so like phase 3 upgrades, which are anticipated sometime in 2034, we are expecting reticle-sized chips with about 1 million pixels, and each chip generating about terabits per second of zero suppressed data. So this is not even full frame data, but this is just zero suppressed data. Okay, so given this grand challenge that we have with LHC detectors, we are looking at how is it that we can do integrated sensing and edge computing. And then we ask ourselves the question, what's the best approach of edge computing? Should we be doing data compression? Should we be doing data filtering? Should we be doing, data featureization? And whatever we choose to do, where should this algorithm be implemented? Should this be near the sensor? Like, for example, a chiplet that is just outside the sensing area? Or should this be, at the edge of the sensor? Like, for example, you have a large readout integrated circuit, and at the edge of the circuit is where you do all the data computation and then only send out the data dependent on the chip bandwidth? Or should you be doing this inside the pixelated area, right at the data source, which would minimize data movement and give us the most power and area efficient solution? However, the constraints for power and area are so high that can we actually end up doing it? And this is what I've been investigating for the last couple of years. And we've tried out several different chips and chip designs for all these 3 different case scenarios. And for today's talk, I'm basically focusing on the at source data processing or within the pixel data processing. Okay. In order for us to, develop an AI algorithm and deploy this within the sensor, Fermilab has developed a HLS4ML framework, which is in collaboration with various other national labs and universities. And this is a silicon-proven method for deploying, going all the way from a physics data, generating an AI algorithm, and then leading to a hardware accelerator. HLS4ML basically allows us to very quickly look at several different versions of the same algorithm, assess the accuracy of and the performance of the solution while being aware of the hardware constraints. So this technique is something that we have tried and tested for various different chips, and this is what we have been using to do most of the work that I'm going to talk about today. Okay. So the current LHC pixel detector, so I'm here focused mainly on the CMS pixel detector. The plan is to have four detector layers closest to the beam pipe. It essentially acts as a vertexing detector. So the smaller the pixels, the higher the resolution. We anticipate, or the one that is the chips that have currently been designed, which are going to lead to the phase 2 upgrades, have roughly about 5 billion pixels, which are across 30,000 chips. And the R&D for phase 2 kind of started in 2012, and the chips are in production now. So you can kind of say there's like a 10-year timeline from when you start off with an initial concept to you start producing reticle size chips. And I think Berkeley is fully aware of this, having been a strong partner for the development of the Atlas inner pixel chips. Going forward for the development or the upgrades that are anticipated in 2034, we've just started doing R&D, and we expect about, times 4 pixelation. So the 5 billion pixels will become about like 20 billion pixels. And if I were to compare between the chip designs for phase 2 upgrades versus phase 3 upgrades, you can kind of see just keeping the same size or an area of the chip, but by reducing the size of the pixel by a factor of 4, you increase the number of pixels by a factor of 4. You want to reduce the detection threshold, because as and how you reduce the detection threshold, and the better physics that you can get out of it. The hit rates we're expecting to be something similar. We also want to see if, instead of reading out the chips at about a megahertz, which is what is currently done, could we use the pixel detector in the LHC trigger applications, in which case you want to read it out at about 40 megahertz, still do not know what the digital buffer size is. Readout links, there's a lot of work that's going on photonic links to replace electrical links. And the radiation tolerance is about the same. And you definitely want to keep the same power consumption, because as and how this detector upgrades, not all the layers of the detector will upgrade. So the powering scheme is likely to remain exactly the same. So these are the constraints hardware constraints that we are starting off with to solve the science problem that I just discussed in my previous slide. Okay, so what is it that we want to achieve? I think what we really want to do is real-time tracking. So here are the 4 layers of the detector, and as and how after a collision, a particle travels through these 4 layers. It depending on the momentum of this particle, it ends up creating a charge cloud in the sensor. And you can kind of see as and how the charges are integrated by the electronics, the shape of the cloud evolves. So our hypothesis is, or at least what we're trying to study is, can we use this cluster shape and this pulse information for filtering out low momentum particles? So could we use a neural network classifier which identifies and save clusters from tracks with high momentum? So say, for example, 2 GeV and above. And if we do this, could we, like, for example, reduce the data by 95% by only saving the high momentum tracks? And could this also be done as a low power implementation? So along with that, there are a few other things that we're looking. So this is the first step of doing data filtering. Then the next step is, could we develop a compact algorithm for going beyond the filtering and doing data reduction through featureization? So essentially, in the vertex detector, you are trying to predict the fine XY coordinate, finer than the pixelation size based on the charge sharing of the cluster of pixels, along with the theta and phi angle, so that instead of sending the raw information, could you actually send predicted information, which could then be used later on, say, for example, in your trigger algorithm and so on. And along with sending the physics information, could we also send out a meaningful error information on the, how confident are we with the decision that we have made? So if we end up doing this, we have a potential for reducing the number of track seeds, which saves time and computing resources down the line. So in order for us to accomplish these two, I think we really require a technology development to enable on-sensor computing. So looking at things like ultra-low power in-memory compute chips, a 3D integration for optimized data processing, and leveraging emerging technologies such as novel CMOS-compatible memristors or resistive RAM in order for us to do energy-efficient computation. So I think in trying to meet these science goals, we will hopefully be able to leverage or push the boundaries of technology and significantly improve the current existing technology. Okay, so I've kind of divided up the talk. I'm mainly starting off with focusing on the algorithm development for the momentum classification, and then I'll move on to the hardware implementation, and then I'll talk very, very briefly, which are our first steps towards featureization. So if anybody is interested, we have put out a smart pixel data set. It's available in Zenodo. I'll try and make these slides available, but this is a clickable link, and you can access our data sets. We have created, I believe, something like 9 or 10 set of data sets, which has been labeled and can be utilized if you want to develop your own algorithms. So the data sets have been generated by interactions in a future pixel detector, which is located at about 30 millimeter radius, operating in a 3.8 Tesla magnetic field. The pixel sizes for the sensor are about 50 by 12.5 micron. The sensor thickness is about 100 micron, and the time steps of this data is about 250 picoseconds. And along with the simulated data, we also have some track parameters that have been taken from the CMS data, from the run-2 data. And we have created these data sets both from the simulated data as well as some real CMS data. For the simulations, we've used time-sliced pixel AV, which is provided by Morris Schwartz from Johns Hopkins. It includes both the electric field and a weighting field to do the simulations. But if you go to this site, you'll get access to the data set as well as all the underlying constraints that were taken into account for generating the data sets. Okay. There is definitely a correlation between cluster shape and momentum. So the first thing that we saw is about that if you just look at the data set, a third of the clusters are associated with tracks. And what we are trying to do is basically reject 2/3 of the clusters that are not associated with tracks. And then with this third of the clusters that are associated with tracks, then we want to reject 95% of those because they are not associated with high momentum tracks. The untracked clusters are mainly due to loopers and broken clusters and other backgrounds. And most of this data associated with untracked clusters are generated from actual data that we are getting from run-2. And basically what we see is that low momentum positively charged tracks increase cluster size. So here you can see this, this is a low momentum track, right? As in how it goes through the detector. You can see it's spread across several different pixels. Low momentum, negatively charged tracks decrease the cluster size. So on the other hand, these tracks which are negatively charged, here you can see there's only like a single pixel that is hit. And then if I were to do a correlation between the cluster size of the pixels versus the position inside this chip. So if you think this chip is like about 2 centimeters wide, with the middle being at 0, 0, and the negative being 1 centimeter and the positive being plus 1 centimeter. So we have a 2 centimeter wide chip. And you look at the number of pixels in the y-axis that were hit. I can plot these 3 plots, which is if my momentum is greater than 3 GeV, this is the line that it follows. If my momentum is less than 3 GeV, but it is positively charged, this is what it looks like. And if the momentum is less than 0.3 GeV, but it is negatively charged, this is what it looks like. So you can see that there's a divergence in behavior and it really strongly matters whether you're positively or negatively charged. And there's a very strong correlation to between Y size, what we call as the number of pixels in the Y direction that was hit, and Y local, which is where exactly on that module was your track passing through. So based on this information, we decided we need to create a multi-level classifier for selecting high momentum tracks. So essentially what we do is we've created a classifier which says 0, that means it is high momentum, -1, it's negatively charged low momentum, +1, positively charged low momentum. So anything that is non-zero is thrown out. Okay. Further, to make this case that we can actually reject 95% of the data, here is the 1/3 of the tracks that we have. And if we plot it, only hits that are reconstructed into tracks are simulated. Then you can see this is the distribution that you end up getting. And if you were to make your cut at 0.2 GeV, you can reject 6%. If you were to make your cut at 2 GeV, you can reject at 94%. If you make your cut at 1 GeV, you can reject at like 70% or so. We are also in the process of generating data sets associated with untracked clusters, which we have really. I just don't have the results documented because it's just it's currently what we are looking at, and we have modified our algorithm from what I'm currently presenting based on the feedback that we received on untracked clusters and how well the algorithm was rejecting untracked clusters. Okay, so this is what we get as a algorithm performance. So we developed 3 different algorithms. One which only took Y size information. So all we did was we counted the number of pixels in the Y axis that was hit, and that is all. That was the only information that was available to the neural network to determine what fraction has been classified as above 0.2 GeV and what fraction has been classified as below 0.2 GeV. So here then this is what we get with Y size. So you can see it's about 80% efficiency for -2 GeV, and there is you are rejecting a lot of data. So you're rejecting something like 78% of the data, but you get something like 13% false positive. So that's something that had to be identified as a low momentum track, got identified as a high momentum track. And there are 20% false negatives, which means the track cluster, which we expected to be identified as a positive or a high momentum cluster, got identified as a low momentum cluster. Then we gave the algorithm a lot more information by giving this Y profile, which basically means that along with the size information, it also had a 2-bit charge information that was available. So below a certain threshold, so we basically had four regions or 2 bits to kind of tell us, where exactly how much charge was deposited inside the pixel. So you can see that it improves the accuracy of the network, especially for the higher momentum tracks. That's where we are interested. Obviously, we are rejecting lesser data, but that's basically because we are accepting more of the good data that we don't want to throw out. And then finally, along with Y profile, we gave the pulse shape information. So timing information, which is the 2-bit ADC value within a 4 nanosecond time period as and how the pulse evolves. So if we do that, we get all the way up to like 99% efficiency, much lower false negatives, much lower false positives, but then we are only rejecting about 60% of data. We were hoping to get to like 95%, but we're getting only up to 60% of data reduction. Okay, so this is basically what we saw with our very first algorithm performance. Then we tried to identify how this algorithm behaves after quantization. So all of this was basically full precision. That means that your algorithm was using something like 16-bit precision for all the values. But instead of full precision, if we do quantization, we are now trying to identify what's happening. So here is the Y profile algorithm. So for all of this, the rest of the work, we kind of did not go forward with the Y size. We are investigating Y profile because it's easiest to do a deep neural network with the digitized data. We're also investigating a spiking neural network for the time slice information. But majority of the slides that I'm going to present, I have a few slides on the SNN, but the majority of the slides I'm going to present will correspond to this black Y profile curve. You can see that it's achieving something like 90% accuracy, or at -2 GeV, and that's where we would like to be ideally, not lose that performance by quantization or hardware implementation. Okay, so here you can see when we quantize it, we get to 90% accuracy with about this 5-bit weights, 10-bit activation, as in how we reduce the bits and the activation, the number of bits of the weights and the number of bits in the activation, the precision goes down. Then we tried a couple of other things, like instead of having a 2-bit quantized model, could we do a 3-bit or a 4-bit quantized model? You can also see, remember this is Y profile, so we are, summing up the values across the Y-axis. So we don't see that if we improve the number of bits, we don't gain too much of performance improvement from that 90%. We also then did, if we change the threshold for the minimum detectable particle, of course, this is set by the noise and the power in your front end. If you had no thresholds, this is just for a case scenario to just show what happens when you have no threshold. The black curve is where you have no threshold. The 400 electron threshold is the blue curve. It's slowly getting there for like the -2 GeV, but it's not as good as a black curve. And then, of course, there's the 600 electron threshold, 800 electron threshold, which are not too far away from the blue curve. So lowering the noise threshold increases slightly the efficiency, but increasing the number of bits does not improve efficiency. I mean, that was our key takeaway from this thing that we studied. Okay, then we also looked at how should we go about actually implementing this. Remember I said that there is a dependence on the local where you are. So sorry, now so this is my Y direction, right? And if I create regions in my Y direction and have a regional network corresponding to that Y region, I can customize my network for that very region and do implement an algorithm that is regional or region aware. And the way we do that is by basically reprogramming the weights of the algorithm. So what we're not doing is we're not creating a new algorithm every time. We actually deploy the exact same algorithm everywhere throughout the chip. But we reprogram the weights inside the neural network across the chip, just so that we can match the or improve the efficiency based on the exactly how the module is placed. So we are expecting something like along the y-axis. So it's 400 times 2. So yeah, 800 pixels. And then along the, 1,600 pixels along the y-axis and about 400 pixels along the x-axis. That's because our pixels are not square. they are rectangular. So the 12.5 micron dimension is along the Y, and the 50 micron dimension is along the X. So if you do this, you can basically divide this up into several different regions. We just chose 64 rows. You can have minimum 16 rows or maximum of 64 rows. You can actually increase this more than 64 rows, and it just depends on. And you can always change this as and how the sensor evolves, or the performance of the sensor evolves. The weights can be reprogrammable. So in our case, a 16 by 16 pixel region corresponds to 8 by 32 readout IC region. That's because the readout IC has square pixels like here, and the sensor pixels are rectangular. So this is a common technique that's used in high energy physics. So for example, if you look at the current phase 2 pixels, a similar approach has been employed there. So if I then take this 16 by 16 region, this is what a superpixel looks like. And my superpixel is where I'm looking for the cluster shapes. So a 16 by 16 region corresponds to one algorithm is deployed in every 16 by 16 regions or areas. Okay, so this is basically what the concept of the implementation is. So we have a single pixel, which is 25 micron by 25 micron. 4 pixels are grouped together. We have an analog island where the analog signal processing is happening, and the blue area is where the digital signal processing or digital data processing is happening. We have 2 different versions of the pixel front end, each occupying a slightly different area, but in general, we have roughly around 0.1 millimeter square area to deploy our entire algorithm for cluster selection inside this superpixel area. Okay, so now moving from the quantized network that we originally came up with to implementing that quantized network on chip. So if we took our very first network, which had 128 neurons with 5-bit weights and 10-bit activation function, we saw that it was taking something like a little more than 300,000 or 0.3 millimeter square area. Okay, and if we set that performance as 100% and then start doing design space exploration to see how we can reduce the area without significantly trading off the performance of the network. So the orange bars show the performance of the network on the same graphs that I was presenting earlier versus the total area. So we started off with 128 neurons, 5-bit weights, 10-bit activation, and we finally ended up with 58 neurons and 4-bit weights and 8-bit activation function, and with a significant reduction in area coming to close to the 0.1 millimeter square area that we are looking for. So this was the design space exploration to make sure that the algorithm actually fits on the pixel and the area that's available inside the pixel. Okay, so here is the original algorithm. We have 14 inputs, which with 6 bits, 14 inputs, and then here's the first dense layer. There's a batch normalization, there's an activation function, there's another dense layer, there's another activation function, and you get the output. So this was the starting solution, and we ended up with this final solution. So essentially what we did was, the aim was to reduce the number of parameters. So here you can see we went from 1920 plus 256. This got merged, and then we reduced it by 256 parameters, and then went from 1920 to 986 parameters with further reduction. And then the other thing that we are trying to do, because we want to do a very low power implementation, is we are eliminating clocking and making the design fully combinatorial. So if I were then to count the number of operations that we need to perform inside this superpixel, which is based on this input being 6 bits and activation weights being around 5 bits. Then if I use a 6-bit integer multiplication, then I need about 75 gigaops per second inside every superpixel. And then if I were to scale this to a full chip, I need to do something like 200 teraops per second per chip. Just to kind of give you a rough idea, I believe the Google TPU does something like 2 to 4 tops per TPU. Okay. Okay, so this was all about the algorithm development, and now I'm kind of going to talk to you about how exactly we implemented this on chip. Okay, so the previous versions of for the phase 2 upgrades, all the designs have used a time over threshold architecture, and we ended up with a synchronous ADC approach because we needed to do 2 things. One is, if we do a time over threshold architecture, what essentially ends up happening is that the charge conversion time is longer than 1 clock cycle. So which basically means that at the end of the frame, so at the end of every 25 nanosecond, if I want to do inference, I need to make sure that I am comparing information from all the different pixels at the exact same time cross, which basically means I need to have a buffer inside the pixel and then have some logic that basically realigns the frame correctly, and then I can do post-processing. So I couldn't go with the time over threshold architecture, and that's why I chose to do the synchronous ADC approach. And essentially what we do is we have 3 comparators. The time over threshold architecture uses a single comparator. Here we use 3 comparators. And by using 3 comparators, we can essentially get 2-bit flash ADC with the conversion that happens within a single bunch crossing clock cycle. And it gives us, the data that comes after this clock period. You can, do further processing without having to worry about, synchronization of any kind. Then, of course, it also has the added advantage that if there's any kind of in-pixel pileup, either not so much so due to signal coming in every 25 nanoseconds, which the probability is fairly low. But say, for example, there are overlapping clusters, and you see small charges from a adjacent overlapping cluster within the same pixel, then there's no way to decouple whether it is 2 signals that you're looking at or a single signal that you're looking at. Whereas in our approach, we are AC coupled between the preamplifier and the ADC, and because we are AC coupled, we can very correctly resolve the 2 hits instead of so we are pileup immune. Okay. The front-end architecture, this is what it looks like. It has a preamplifier, a feedback, a very traditional preamplifier with a leakage current compensation circuit, and a 3-bit ADC or a 2-bit ADC using 3 comparators. We have 2 different implementation. One is a single-ended, and the other one is a differential. So we do have 2 different prototypes. One that does auto zeroing, so using a dynamic comparator, and then there's another one which is a static with a couple of bits of trimming so you don't have to do a dynamic comparison. Okay, so this is what the preamplifier looks like. We have 2 modes of operation, one with the lower power and the other one with a slightly higher power. This is all designed in the 28 nanometer process. So obviously the higher power has better noise performance, but basically the front end works like a traditional preamplifier front end. Then we have a single-ended versus a differential dynamic comparator. Again, the total power of the pixel, so this includes the power of the preamplifier plus the 3 comparators. In the single-ended version is 3.7 microwatt. In the differential version is about 5.2 microwatt. And then we, I think if we do something like a 5 sigma setting of the threshold, you might be able to come to like 400 electrons. The chips are currently back. We are expecting the boards to be back soon as well. And we're in the process of testing and qualifying the front end. Okay. Right. This is what the layout looks like. This is the analog island, and the periphery is where all the digital goes in. So now that we have the algorithm, this is what the HLS implementation looks like. So this first area here is batch normalization. This is where the activation function is. This is the dense layer, the second dense layer, and then this is the last softmax function. Okay, so here is what the super pixel looks like. So this is 16 by 16 sensor pixels or 8 by 32 readout IC pixels. Here you can kind of see these are the analog islands with all the power distribution, and the highlighted red region is the digital algorithm or the data classifier algorithm. And then if I highlight the registers, which are storing the weights, the white highlighted areas are all the registers. Yeah, we plan to do full triple modular redundancy for SE mitigation. Okay, so yeah, the first chip was taped out. We are expecting a second tape out in 2023. I mean, next month. It's actually 1st of June, 31st of May. So I would call it 1st of June, where we integrate both the algorithm as well as the front end. So currently, the chip that is back only has the front end, doesn't have the algorithm. And at a later step, what we plan to do is have multiple. So in this one, it has 2 super pixels. So this is a 16 by 32 implementation. So it has 2 super pixels, but eventually we plan to do a larger chip with multiple super pixels, and then put in the data featureization algorithm on the periphery. Okay, so I'm going to shift focus a bit from the implementation and over to my last topic of algorithm development for featureization. And here, what we are trying to do is predicting XY, angle of coincidence, angle of incidence on the sensor. So for example, this is where your particle traveled through. So you just don't want the address of this pixel, but you want a finer XY resolution. And essentially you can get that by looking at the charge cluster and extrapolating, depending on the charge sharing in the neighboring algorithms, you can extrapolate and kind of give a finer XY resolution. Okay, and then we also want to do angle of incidence to the sensor, perpendicular and in the bending plane of the magnet. So this is the alpha and beta, just so that the 3D tracking algorithms, which are computationally expensive, grows with the number of possible combination of hits. So you can, if you are able to give it the direction in which it should be looking out for, then you can, not see. So say, for example, these are the hits that you get from, say, the 3 levels. And if you were able to, along with giving, saying that this is a high momentum track, if you were able to give that the angle, the most probable angle. So not only do you give an angle, but you give a probability of the validity of this angle, then you can look at a cone and then, try and pick out from these whether, the line forms through this one or the line forms through that one. But now you are, reducing the number of permutation and combinations that you have for track finding. Okay. So here are some of our the very early algorithm. So you can kind of see this one here. This is the full precision, the blue one, and then of course the orange one is full precision with time, and the green one is the quantized algorithm. You don't see it so much here, but you can kind of see this in this plot where you're looking at the variance, and you see that the full precision with time gives you the best performance, right? You can actually also see the 2 peaks associated with it. The first peak is when the track is not going through middle of the pixel, So when it doesn't go through the middle of the pixel, then you have a lot more charge sharing information. So you get this first peak. And then you get the second peak when the track is going right through the center. And this is for the X direction, and the X direction has 50 micron. And yeah, so this is the full precision with time. This is the full precision, without time. And then this is the quantized model. And here is the uncertainty of that prediction. You can see the same plots that we've made for the y-axis, the y direction. So this is for the X, and here is for the Y. Again, the algorithms perform much better when they are when they have the time information, and as and how they get quantized, their performance, deteriorates. So and here is the uncertainty associated with it. These are all preliminary results, and actually I'm not the best person to kind of give more information about it, but Janet, Gauri, and Lindsay at Fermilab are the ones who are working on this. Feel free to reach out to them. I'm happy to connect you with them as well if you want more information on how we are doing both the prediction as well as the uncertainty. I'm more involved in how do you implement a UQ algorithm on chip as opposed to how do you develop a UQ algorithm. Okay, so we're doing something similar for the alpha from the X profile, and then again alpha with the X profile with time, and then you kind of see with the time you have and the uncertainty is less than 10 degrees. Sorry, without the time, you have uncertainty, which is less than 10 degrees, which is still really good. And then with time, the uncertainty is less than 7 degrees. And then you can also see, the performance degrades beyond 60 degrees. And there's a strong correlation between the angle of incidence and the X size, as in the number of pixels that were hit in the X direction. Okay. Similar results for beta. So this is, I believe one is in plane and the other one is perpendicular. So yeah, again, 1 sigma uncertainty is about 5 degrees and then with timing information, you always are doing better. Okay, so some implementation ideas about the featureization. Of course, you have this option of doing like an AI chiplet just at the, so you determine what are the high momentum clusters. You shift out the high momentum clusters off the chip, and then you can use a very advanced geometry node, like, or go all the way up to 3 nanometer and implement that as an AI chiplet, and then utilize that to do your featureization. It has the highest overhead associated with power consumption, essentially because you still require these high-speed links to transfer data from the chip to the chiplet. So this is the highest cost consumption, but it's here because AI chiplet design is so popular these days, and everybody in the industry is looking at chiplet design. So yeah, I had to kind of make a case for what would it look like if you were to use an AI chiplet. You can of course do it on the edge. So like say, for example, divide it up into several columns and have multiple copies of a featureization algorithm instantiated at the end of the column. And, you can use the exact same technology node because it's in the periphery. You can use higher speeds. So you could possibly, run this at a much higher rate than the 40 megahertz and have some amount of buffer so that you can, do this. So this is definitely a really good solution, and definitely the solution that we want to start off with anyway. Looking in more forward direction, you can think about a 3D IC where you're doing, the data classifier on a level 1 chip, and then you can do a data classifier on a second chip, which is 3D integrated. on a higher level, then you can, of course, choose a different technology node and stuff like that. And you can, essentially slow this down because you can do massively parallel compute. So you wouldn't do anything more than 40 megahertz clock, and you can go back to doing this fully combinatorial without having a high-speed clock that you would require for something in the. So this is essentially, we believe, could be the lowest power type of implementation. Okay, I think with that, I have a few slides just because of this neuromorphic implementation. So how do you exploit the time information? So one of the things that we are studying is essentially using a neuromorphic front-end concept based on this dynamic vision sensors, which is a very mature development out there. So we are borrowing from the neuromorphic community that kind of does this. The big difference for us compared to what is out there in the industry and where these are typically used is that the time scales where these dynamic vision sensors have been designed is more, in the millisecond time regime. In our case, we are in, a few nanoseconds, and we are kind of trying to do ultra fast signal processing. So when you do something of that sort, and you kind of, so if I just take a model, right, like a VCVS kind of a source without putting in a transistor circuit together, you can see this time frame here. This is like a few. It's 4 nanoseconds from start of the waveform to the end of the waveform. So essentially, you're producing these spikes at a few hundreds of picoseconds. And there are a lot of difficulties when you're trying to not only produce the spikes at a few hundred picoseconds, but also process spikes at a few hundred picoseconds. One biggest thing that I can just see off as like an analog designer in the front end is how do you implement such a fast reset so that you can, integrate the charge, quickly reset it, and be ready while the signal is still climbing. Of course, you can change the bandwidth of your TIA and make it really slow. But then when you do that, you're not optimized for noise. And if you're, trying to optimize it for speed, you can, again, also do another thing, insert a pulse shaper in between the TIA and the next stage to delay things. But yeah, still not a very ideal case scenario, just because, hundreds of picoseconds. If I want, I can stretch it over a few tens of nanoseconds, but probably not more than that. Okay, when I then kind of, said, okay, if I don't do this, but I'm essentially modulating the pulse width that is generated, so all of these on spikes correspond to a single pulse, and the off spikes correspond to another large pulse. But instead of it being a digital pulse, now it's a semi-analog pulse, because the width of the pulse matters, and not just the number of pulses. That is like a analog neuromorphic technique, which we are thinking of exploiting, just so that we can get the best of the two worlds. And then I was also told that even if I manage to create these spikes at 100 picoseconds, there are no neuromorphic. Okay, our first implementation is like a digital SNN implementation, but eventually we would like to gear up towards like a memristor-based implementation. And then I was told that there are no memristor materials that are available which can respond to spike trains that are happening at such a high rate. So the hardware, or even the new materials for the new futuristic hardware, does not exist. So that would be an overkill. And that's the reason why we are trying to do this in a semi-analog fashion. Okay, so this work was done in collaboration with Oak Ridge National Lab. And essentially what we are trying to do is creating a spike train through a spiking neural network where we get spikes in time, or pulses. In our case, these pulses that we are generating are in the order of nanoseconds. So now this you can see is like roughly around 1 nanosecond, and this one is roughly around 2 nanoseconds. So Yeah, so you have a synapse, and then you have a threshold. So you have an input train of spikes, which corresponds to an output train of spike based on how the algorithm is trained and what are the weights that you are using, and what the style of the neuron that you have developed. So these networks are inherently temporal. Neurons fire with, whenever you exceed the threshold. There are multiple ways to tune parameters. You can, of course, tune the synaptic weights. You can change the neuronal thresholds. You can also tune the network architecture. We are looking for, it looks like a promising solution for energy efficient, area constrained systems. Here is an evolutionary optimization method for training neuromorphic networks. And this is what we are essentially doing. We take the sensor waveform, we create a set of spikes, we actually oversample so that we don't miss any spikes. So once the signal crosses every 400 electrons, and we've done several different variations with spikes, with pulses. Both of them appear to be, very similar. And then we can send it through a classifier network and use a cost fitness function to, penalize the network when it's not doing what you want it to do, and then have some sort of like a learning rule so that you can come up with a set of networks that you can play with or implement on chip. When we first started off, we were, not going above 60% efficiency. So no matter what happened, we weren't getting there. The time to train these networks increased. We added a greater number of neurons. We tried out different training methods, and it wasn't getting there. Then we did the exact same thing. So the Y profile information. So instead of looking at the two-dimensional image of the 16 by 16 cluster, we did the exact same thing of a Y profile information, as in summing across. So creating a stride across, the 16 channels. And that kind of improved a little bit, but also did not, get beyond a certain level. Then we added a penalty function. So basically to say anything which has been classified as was supposed to be a high PT cluster and got classified as a low PT cluster, penalize the network and penalize the system and update the training. So when we did that, we came up to almost 100% efficiency. But then of course, the prediction, so our testing score went up, but then we were also allowing a lot of low momentum tracks to just go through. So we were rejecting, less than 6% or 12% of the total samples. So yeah, we went to one other extreme. Then we did a few other things. Yeah.
I'm sorry to interrupt you. We really are running out of time. Would you be able to start wrapping up so we can take questions?
Yeah. Two more slides. That. Yeah, no worries. I should monitor the time more carefully. Yeah. So now we are closer to 91%. The data rejection is 20%. The neural network for SNNs is a bit harder to train. We've actually just last week increased this accuracy because they've tried out a completely new framework called DEFI, and I don't have slides on that, but we went up from 19% all the way to 40%. So we're slowly getting there, and but we have a first implementation. Eventually, the plan is to also use neuromorphic materials along with the neuromorphic algorithms. And I think with that, at the end, of course, this work leveraged a lot of people and a large collaboration of colleagues from across several institutions. And sorry for going over time, but thank you. And I can take any questions here.
Thank you very much. We maybe have time for one question from the room and one from Zoom. Anyone in the room have any burning questions? Not at all. Okay, I'll ask one very quickly then. I saw that you late last year had a really interesting paper on this chip you developed for the CMS calorimeter that uses a lot of these principles called the Econ-T, and I was just wondering how your experience developing that chip informed the work you're planning to do with the pixel detectors.
Yeah. So I mean, yeah, that's pretty much like a chiplet concept, right? So that's a data concentrator chip. So you're getting in data from different front end designs, actually 42 different front end pixels into a data concentrator chip, and then actually we designed our methodology of going from the algorithm to accelerator for econ, and we've very successfully tested econ. Got very good promising results. Econ does the exact same thing with programmable weights. So you can customize it based on the detector geometries that we can see in different areas of the detector. Even in Econ, the number of bits that was coming in from the front end was something like 22 bits. We did do some pre-processing to convert from 22 bits down to 8 bits, just so that we wanted to keep a compact neural network. And this is exactly the same thing that we are doing here. So instead of looking at the image with 256 inputs, we sum across the columns and create a 16-bit input so that the network is very manageable. So yes, so all of that fed into the work that we are doing here by, understanding the pros and cons of doing things like normalization, pre-processing, and how to build smaller networks. Yeah. Thanks for the question.
Thank you very much. Anyone on Zoom, please raise your hand. Okay, I'm not seeing anything. Well, unfortunately, we've run out of time, but thank you so much, Farah. It was very detailed talk, and we're looking forward to seeing the results of the chip. Thank you.
Thank you. Thanks a lot.